In chapter 3, we're going to talk about linear motion, and linear is just a fancy word that means straight line motion. The kind of motion you would have if you're driving down a straight highway, or if you drop an object and it falls straight down. One of the first ideas we want to talk about is relative motion. Everything in the universe is moving. The Earth is moving, our solar system is moving, the Milky Way is moving. Okay? So anytime we talk about motion, we're talking about motion relative to something else. Most of the time we talk about motion relative to the Earth because we tend to think of the Earth as being fixed, even though it's not. As I stand here, I am moving 107,000 kilometers per hour relative to the sun. So are you, so is the whole planet. However, I'm not moving at all relative to the Earth. I'm standing still. Okay? If you were to get on a bus, and so let's suppose this bus is traveling 50 miles an hour east. And that's his speed relative to the highway or relative to the Earth. If you're sitting on the bus, you're also traveling 50 miles per hour east. But if you decide to get up and walk to the front of the bus, and you walk to the front, at 3 meters per second, I'm sorry, not meters per second, 3 miles per hour, then that's your speed relative to the bus. To somebody who's not on the bus outside, it actually looks like you would be walking 53 miles per hour. Also to the east, if you're walking to the front of the bus, you're walking in the direction the bus is traveling, relative to the Earth or relative to the ground. Okay? Maybe you walked to the front of the bus, you wanted to tell the bus driver something. Maybe you asked him out on a date and he turned you down flat. So you turn around and you make a beeline back to your seat so that if you walk to the back of the bus, and this time you're walking at 5 miles per hour, but you're walking in the opposite direction the bus is traveling, well, you're walking 5 miles per hour relative to the bus is going 50 miles per hour to the east. You are going 5 miles per hour actually towards the west, so you end up with a speed of 45 miles per hour east relative to the ground. Okay? You can picture these if you want. If the bus is going 50 miles per hour and you go 3 relative to the bus, you can see that gives you a total speed there of 53 miles per hour relative to the ground. However, if the bus is going 50 and you turn around and walk 5, the net effect is that you're only going to go 45 miles per hour. Relative to the ground. So we just want to keep in mind all motion is relative, but most of the time when we talk about motion, we're talking about motion relative to the Earth that we think of as being fixed. The next concept we want to talk about is an average speed. Most of us are pretty comfortable with the concept of average speed. If I want to calculate my average speed, it's just going to be that total distance that's covered divided by the time. Speed and velocity are really closely related in physics. We'll talk what the difference is in just a few minutes. But equation normally looks something like this, that our average velocity is equal to distance divided by time. If I'm going to measure distance divided by time, there's a lot of possible units. It could be miles divided by hours. That's a common one we use a lot in our everyday life when we drive. But it can also be meters per second. That one is what we call the SI unit or the metric unit. That's what most of our measurements in physics are going to be based on. So most of the time when we're talking about distances, we're going to talk in meters. When we talk about time, we're going to talk in seconds. But that can vary. There's no wrong units. There's just different possible units. Okay. Now, if I take this average velocity formula and I rearrange it, I get a formula that says distance is equal to velocity times time. You may remember that one even from, say, middle school as distance equals rate times time. So we know that if we're going at 50 miles per hour and we travel for 3 hours, we'll cover a distance of 150 miles. So that equation, this equation, they should be really pretty familiar to you. But let's switch from this idea of speed, which is something we're familiar with, to the idea of velocity. Velocity is speed with direction. So the thing that separates velocity from speed and how they're different is direction, okay? If you look at your speedometer in your car, it's going to tell you your speed, how fast you're going. But if your car also has a compass, then you can figure out your velocity. You'll know how fast you're going and you'll know in what direction you're going. Velocity I'm getting ahead of myself, and I don't want to get ahead of myself. No, I'm not ahead. All right. Velocity is a vector. Now, vectors are measurements or quantities that also have direction. We normally say that a vector has magnitude Magnitude's just another big word, and the only thing it means is size, that it has some numerical value or size. A vector has magnitude and direction. So, an example of a velocity vector might be that v equals 15 meters per second up. There's lots of ways to say direction. Up, down, left, right, northeast, southwest. There's all kinds, but it has to have a direction. Okay. Speed, on the other hand, which we talked about first, is a scalar quantity. Scalar quantities don't have a direction. Okay? Scalars only have magnitude. There's a lot of measurements that we're going to talk about that are scalar measurements. One example will be mass. If something has a mass of 3 kilograms, its mass does not point up or down or left or right or north or south. Doesn't make any sense. Time is a scalar quantity. Energy is a scalar quantity. But other things that we talk about will be vectors because the direction will be very important. Velocity, acceleration, force, momentum. So those are things we'll be talking about that are vectors. One of the things I want you to do as you study is make sure you know which quantities that we've talked about are vector quantities and which ones we've talked about are scalar. So far, we've talked about velocity and speed. That one's easy because velocity is a vector and speed is a scalar. So our letters came out just right. There's 3 ways that you can change your velocity. Let's just back up a little farther. A constant velocity, and sometimes they use the words uniform. Probably use constant more. A constant velocity or uniform velocity means that the velocity is not changing. Well, how can velocity change? Constant velocity has a constant speed in a straight line. Okay? Constant speed in a straight line. There are basically 3 ways velocity can change. You can speed up. If you want to think about being in a car and driving down a long, straight highway, even though the highway is perfectly straight, if you speed up, your velocity is changing. You can slow down. Same thing, you can be on a perfectly straight highway, but if you let up on the gas or you start to use your brakes, you're going to slow down. Or you can change direction. If you do any of those things, you are going to change your velocity. Velocity is speed with direction. If you change your speed, whether you're getting faster or slower, or if you change direction. So you can be going at a constant 50 miles an hour, but if you go around a curve, your velocity is changing because your direction is changing. If we go back to chapter 2, our previous chapter, just kind of a refresher, when something has a constant or uniform velocity speed in a straight line, according to Newton's law, first law, the net force is 0. Or you can write that as the sum of the forces. That means net force is 0. So if you're traveling at a constant velocity, you're traveling in a straight line at a constant speed, the net force acting on you is 0. However, if your velocity is changing, in order to speed up, slow down, or change direction, you're going to have a force acting on you. And if you have a net force acting on you, you will be accelerating. If any of these things are happening, they're all considered acceleration. A lot of times in our everyday language, we think of acceleration as always speeding up. But in physics, acceleration doesn't just mean speeding up. If you slow down, that's an acceleration. If you change direction, that's an acceleration. Anything that changes from a constant velocity, anything that changes that is going to be an acceleration, and it's going to require that you have a net force that's not zero acting on it. So let's look a little closer at this idea of acceleration. Acceleration tells us how quickly the velocity is changing. Now, a lot of students have trouble with the difference between speed, velocity, and acceleration. Speed tells us how fast you're going. Maybe you're going 25 meters per second, maybe you're going 1,000 kilometers per hour. But speed tells you how fast we're going. Velocity tells you how fast you're going and in what direction. Okay? Acceleration is really fairly different. Acceleration is the rate that the velocity changes. It's how quickly or slowly the velocity changes. You can have a very large velocity, like 1,000 kilometers per hour, that's changing very slowly. So you can have a very small acceleration. Or you can have a very small velocity. Maybe you're going 2 meters per second, but it's changing very quickly so that just a few seconds later, you're going hundreds of meters per second. Okay? Very different things. Velocity tells you how fast you're going and in what direction, but acceleration tells you how quickly your velocity is changing. If we write it as a formula, it's going to look like this. Acceleration is equal to the change in velocity divided by the time interval. How long did it take for that change to happen? So, if we write it symbolically, we use an A for acceleration, change in velocity, change in time. Those little triangles mean the change in that quantity or the difference in the before and after. So, change in velocity, change in time. If we want to think about an example, suppose that you're in a car and you're going 50 miles per hour and you brake to a stop. Well, you were going 50 miles per hour, now you're going 0. That tells me your velocity changed by 50 miles per hour. If it took you 20 seconds for that change to happen, well, if I do 50 divided by 20, it comes out to be 2.5. My units look unusual because I've got miles per hour per second. But that's exactly what it means. It means my speed changed 2.5 miles per hour every second. My velocity changed by 2.5 miles per hour each second. So if I was going 50 and I'm braking, well, 1 second later, I'm going to be going 47.5 miles an hour because I lost 2.5. 2 seconds later, I'm going to be going 45 miles per hour. It's changing that much each second. Okay, I want to talk about a really specific type of constant acceleration, or one that you're probably somewhat familiar with, and that's the idea of free fall. If I take one of these markers and I drop it, it's going to fall straight down towards the center of the earth, and we call that free fall. And objects in free fall, because of the force of gravity, right? That's why things fall. When we say free fall, we basically mean gravity is the only force. Means we can totally ignore any type of air resistance, any type of friction. There's absolutely no other force acting on it. Real simply, if I drop both of these, one of the things that you'll notice, of course, let me get a blank sheet of paper. If I drop both this marker and this piece of paper, it's going to be really obvious that the marker's in free fall. But this sheet of paper is very much affected by air resistance. That's not free fall. Any situation where you cannot ignore air resistance is not going to qualify as free fall. But now if I wad this piece of paper up, I can get rid of a lot of surface area. When I get rid of this surface area, it pretty much makes it go in free fall. Notice this time they'll probably hit the table at the same time. They did. Okay, so one of the criteria is that gravity must be the only force. If you have to take into account air resistance or any upward forces, it's not truly going to be free fall. Okay. Interesting thing about free fall is as long as we are roughly 1 Earth radius from the center of the Earth, 1 Earth radius is the distance from the center of the Earth to the surface, the acceleration of the force is going to be the same on all objects. And that's true even if you go, I don't know, a couple hundred miles straight up. You're still going to be roughly at the same height from the center of the Earth. Near Earth's surface, all objects fall with a constant acceleration of 10 meters per second per second. Now we don't usually write 10 meters per second, but that is an acceleration. Your speed when you drop something changes by 10 meters per second each second. We normally write it as, we represent it with a lowercase g. That's called the acceleration due to gravity. It's a lowercase g. G is equal to 10 meters per second squared. In this class, we'll use that number probably 99%, if not 100% of the time for G. However, if you were taking Physics 24-25, where we need a greater amount of precision when we do our math, we would use the fact that at Earth's surface, it's really closer to 9.8 meters per second squared. This one's more precise, but we don't really need that level of precision to understand what's going on. We're more interested in understanding how does gravity behave than precisely how fast something is falling. What this means is if I drop something, every second that it falls, it's going to gain 10 meters per second squared. So let's say, for example, let's think of some examples. Let's suppose I drop a rock off a high cliff. And it lands six seconds later. All right, let's just look at how fast it's falling. We'll even make a table, because sometimes tables really help us understand what's going on. Here's the time, here's the velocity or the speed. We know the direction's down, so it's a speed downward in this case. When I drop something at t equals 0, its velocity is 0. That's different than if I throw it up or if I throw it down. If I just drop it, it starts with a speed of 0 or a velocity of 0. We know the acceleration is 10 meters per second each second. So 1 second later, it's going to be going 10 meters per second. If you want to remind yourself it's going down, we can. If I wait another second, this speed will also be 10 meters. It will be 20 meters per second. Why? Because the acceleration is a constant. It's gaining g, or the acceleration is g, 10 meters per second each second. That's what an acceleration is. It tells you how quickly is the speed changing. In free fall, it's 10 meters per second squared, or 10 meters per second each second. So I wait another second, it's falling at 30. I wait another second, it's falling at 40. By the time it's fallen for 6 seconds, it's reached a speed of 60 meters per second. Now, as soon as it hits the ground, it's going to stop, obviously. So usually when we ask, what was the speed when it struck the ground, or right before it struck the ground, we don't mean 0. We don't want to know that once it hit the ground, it quit moving. We want to know how fast was it going when that happened. So you can see it's really easy to figure out how fast. If you knew how long it takes to fall, you can easily figure out how fast it's going. Think about it a little bit differently. What if we don't just drop something? What if we do throw it straight upward? If I throw it straight upward, what if I going to let it be in the air a good bit longer. It's going to take 12 seconds, and I actually threw it up. So someone helps to visualize this. So here's my tall cliff. Here's my rock, and I'm throwing it up. I'm going to stick my arm out over the edge of the cliff just a little bit because I'm going to throw it up. I know at some point it's going to reach a maximum height, and then it's going to fall all the way back down till it hits the ground. And I'm standing there, and I got my stopwatch, and I hear it hit the ground. I know it took 12 seconds. Let's think about what's going on with velocity. And again, if we understand how the speed changes 10 meters per second, each second, this isn't going to be too hard. I do have to pay really careful attention, though, to direction. Velocity is a vector. Acceleration is also a vector. Acceleration has a direction. The acceleration due to gravity is down. Most of the time, if we're trying to solve a problem like this, we need to decide. We usually let up be positive and down be negative. I didn't worry about it when I was just dropping something because I knew everything was moving down. But if I'm going to throw something up, I'm going to have a velocity that's upward, but I'm going to have an acceleration that's downward. One of the things that we'll realize is any time velocity and acceleration are pointing in opposite directions, the speed decreases. So let's make a table just like we did before. And let's see what's going to happen. This time, in fact, I'm going to make a third column. This is going to be in meters per second. And this is going to be in meters per second squared, or meters per second per second. And I'm going to do 1, 2, 3, 4, 5, 6. I'm going to have a second table because it's in the air 12 seconds. 7, 8, 9, 10, 11, 12. Again, time. This is the speed, the velocity in meters per second. And this is going to be the acceleration, which of course is meters per second squared. Now, one of the first things I want you to understand is when something's in free fall, the acceleration due to gravity is constant. It is a constant 10 meters per second squared downward. This third column is never going to change. So, we threw it up at 30 meters per second. The acceleration is a constant 10 meters per second, but I have to call that a negative 10. If I'm going to consider throwing something upward to be in a positive direction, then an acceleration that acts downward is going to be negative. After 1 second, 30, it's going to lose 10. It's going to be going 20. Well, that makes sense. When you throw something up, it slows down. If I wait another second, it'll be going 10. At 3 seconds, the velocity is going to be 0. That's this point right there. V equals 0 at the maximum height. So we reached a maximum height after 3 seconds. This acceleration due to gravity is a constant negative 10. Even if the velocity is 0, that doesn't change the fact that gravity is exerting a force, and that force is accelerating the mass at 10 meters per second downward, or 10 meters per second squared. If we wait another second, the velocity will be negative 10. Then negative 20, negative 30. Notice after 6 seconds, it's right here. It took 3 seconds to get to here, and it took 3 more seconds to get right back to there. Acceleration never changes. At 7 seconds, it's at negative 40, negative 50, negative 60, negative 70, negative 80, negative 90. The acceleration is negative 10 all the time. Now, you'll notice it's moving fastest right before it hits the ground. Anytime you have a negative velocity and a negative acceleration, you're speeding up. If you have a positive velocity and a positive acceleration, you're speeding up. Anytime velocity and acceleration point in the same direction, so they have the same sign, you're getting faster. Anytime, like what was happening here in the first 3 seconds, anytime you have a positive velocity and a negative acceleration, you're going to slow down. So that's one to just maybe make a note of. If velocity and acceleration are in the same direction, you'll get faster. If velocity and acceleration are in opposite directions, you'll get slower. Now, the one thing we haven't talked about is how far is this object going to fall? If we want to find distance, and I don't want to find distance where I throw something up, but I can certainly find distance where I just drop something. For an object at rest, starting from rest, let me put it like that. For an object starting at rest, which is what happens when you drop something, the distance that it travels is 1/2 its acceleration times the time squared, which for free fall turns into 1/2 g, that's the acceleration due to gravity, t squared, but we know that g is 10. If I put in my 10 there, for free fall, this would be for the distance for a dropped object in free fall. So if I know how long it took to fall, now I can't throw it up or throw it down. This formula strictly works when something starts from rest. But in that first situation where I dropped it and I heard it fall for 6 seconds, if t equals 6, then the distance is going to be 5 times 6 squared. Well, that's going to be 5 times 36, or 180 meters. So if it took 6 seconds to drop, if you drop it and you hear it hit the ground in 6 seconds, as long as you know air resistance isn't a factor, you know it fell 180 meters. In fact, let's just make a little table, because these first few values kind of come up a lot. If I drop something, so we're going to drop from rest. And we'll go ahead this time, since we're dropping it, we'll just let the acceleration downward, we'll treat down as positive. Everything's going to fall down, fall in a positive direction. The acceleration is going to be a constant 10 meters per second squared. That number never changes. Just look at the first 4. If I want to know the velocity in meters per second, it's going to start off at 0. 1 second later, it's going to be going 10. At 2 seconds, it'll be going 20. At 3 seconds, it'll be going 30. And at 4 seconds, it'll be going 40 meters per second. So we see this velocity increasing at a constant rate of 10 meters per second. Now, the distance is not going to be that constant. When something's accelerating, it travels longer for each second that goes by. So Remember, the distance is 5t squared. Well, at t equals 0, that's 0. At t equal 1, 1 squared is 1, 5 times 1. It falls 5 meters in that first second. A lot of students are real tempted to think somehow that it should fall 10 meters per second because it's going 10 meters per second at the end of the first second. But remember, at the beginning of that first second, it was going 0. Well, the average between 10 and 0 is 5. So it actually only falls 5 meters during that first second. If I plug in t equal 2, if I do 2 squared, that's 4 times 5, we see it equals 20. Notice in the first second it only fell 5 meters. But in the second second, it fell 15 meters for a total distance of 20 meters. If I do 5 times 3 squared, that's 45. And finally, if I do 5 times 4 squared, that's 80. If we were to picture this, it's going to look something like this total, let's suppose this total distance is 80. It took, there's 80 meters. Half it, that's 40, 20, 60. I'm just kind of spacing it out. In the first second, it only fell about that far. That's that 1 second. Okay? By 2 seconds, it had made it to the 20 meter mark. So here we'll do this. There's 0 meters, 5 meters, 20 meters, 45 meters, and then 80 meters. You can see for each second it's traveling a greater distance because it's going much quicker during this 4th second than it was going during this 1st second. If you understand this table, you probably have a pretty good handle on free fall. We're going to look one more time at the idea of velocity vectors. Be sure to read through the PowerPoint. They give some different examples. And if you look through the PowerPoint provided by Pearson, they will also give you possibly some different examples with multiple choice. The notes part in the Pearson PowerPoint is kind of skeletal, but it's got some good multiple choice questions to think about as you read through it. All right, we talked about that problem on the bus, but when we talked about the problem on the bus, you were either going in the same direction as the bus or you were going in the opposite direction of the bus. A lot of times in real life, we have a situation that's slightly different. Suppose that we have a situation where perhaps we know that I'm going to do the one, let me make up one. Suppose you're trying to cross a river. Here's a river. And this river has a current. And the current is going this way at 6 meters per second. Every second that you put a boat in here, it's going to get pushed down relative to the shore at 6 meters per second. What if you get in a rowboat and you start rowing across? Here's your boat, you're going to start at this shore. You're going to row across at 8 meters per second. You won't land right here because you won't actually be traveling 8 meters directly across. We need to add those vectors together, okay? Now, if you were trying to row downstream, you were going, well, let's do that direction. Let's just start, let's do all 3. If you're in a boat and you're rowing 8 meters per second this way, and the current is taking you 6 meters per second, the sum of those velocities, because they're in the same direction, are going to be 6 meters per second plus 8 meters per second, which is 14 meters per second downstream. Okay, what if you didn't want to go downstream? This will be a lot harder. What if you need to go upstream, but you're still only rowing at 8 meters per second? Well, now they're going in opposite directions. Anytime you're trying to combine vectors that are going in opposite directions, you actually end up subtracting. We have to consider this to be a positive 8 meters per second. This would be downstream would be a negative 6 meters per second. And the result is you would end up going 2 meters per second upstream. You can see here why direction with vectors is so important. Whether those velocities are in the same direction or opposite directions has a huge impact on the result and what actually happens. Well, let's suppose you're not trying to row upstream or downstream, but you're actually trying to get across the river. So you get in your boat and you start rowing directly across the river at 8 meters per second. If I want to add those two velocities, they are perpendicular to each other. Anytime I want to add perpendicular vectors, I'm going to use the Pythagorean theorem. I could draw them if I wanted to. Here's what I've got. I've got 6 meters per second this way, and I'm also going 8 meters per second that way. What I want to find out is called the resultant. A resultant just means the sum of two vectors. I know I'm going to end up going this way. This boat isn't going to go straight across. It's going to be pushed downstream because of that 6 meters per second down. The solution to those types of problems that involve a resultant are found with the Pythagorean theorem. I would say 6 squared plus 8 squared has to equal the resultant squared. That's a squared plus b squared equals c squared. So I've got 36 plus 64 is r squared. 100 is r squared. To get r, I have to take a square root. 100 is an easy one to take a square root. That's going to give me r equals 10 meters per second. So he actually ends up going a little faster than the 8 meters per second. Doesn't go as fast as the 14 when he was going downstream, but he goes faster than just the 8 because this is adding to his speed. Now, that one's a pretty easy one. Let's do one more of those. I put an example in the PowerPoint where I talk about an airplane. And in this case, we've got a plane that's traveling 200 kilometers per hour north relative to the surrounding air. So his plane is moving that much faster than the air that surrounds the plane. However, there's a big wind. So the wind is actually moving all of that air. Just like water that's flowing downstream, the wind is blowing, that's a crosswind blowing at 60 kilometers per hour. It doesn't tell me whether it's going east or west, but a crosswind means it's going perpendicular. The result is, instead of going up 200, he's going to go up 200, and he's going to go over 60 kilometers per hour. And he's going to end up traveling not the way he meant to go, but like that. Of course, pilots correct for crosswind, so they don't actually get off course. But relative to the ground, if you're going 200 kilometers per hour north and 60 kilometers per hour to the east. When we do the Pythagorean theorem, we get 200 squared plus 60 squared equals that resultant squared. This is going to be 40,000. That's going to be 3,600. So 43600. I just have to take the square root of that. And when I take the square root of that, I get that R is equal to about 208.8 kilometers per hour. Notice it doesn't have quite as much effect as you might have expected, but it definitely is adding to his speed, and it's definitely taking him off course. If this was in Mastering Physics and they said write your answer to 2 significant digits, then you would write that it was to 2 significant digits, 210 kilometers per hour. We would round that to the first 2 digits. If it says write that answer in 3 significant digits, then we would have written 209 kilometers per hour. Okay. It's really important that when we're dealing with vectors, we realize that that direction makes a difference. That's all I want to say about Chapter 3. If you have any questions after watching this video and after working on the homework, please email me or pass them at a Collaborate meeting. The questions you have, other students also have. And I'll see you in the next video.